Every year, billions of people around the world press the same pedal, and they don't even realize it was slowly killing them for decades. What was supposed to save lives quietly filled the air with poison. Why did a material once considered perfect vanish almost overnight? And what replaced it? There's one detail brake pad ads never mention, but it's what determines whether your car stops in that critical split second. Today, these pads withstand hell itself, don't smoke, and leave barely a trace. But the road here was deadly dangerous. Stick around till the end, and you'll discover which hidden component once cost millions of lives and why modern factories guard their formulas like state secrets. In the 1920s, every brake pad contained asbestos, fibers that could handle 1500 degrees Fahrenheit and wouldn't wear out. But every tap of the pedal released microns of poison into the air, settling in the lungs of drivers and pedestrians. By the 1990s, asbestos had killed millions. Lung cancer, mesothelioma. Europe banned it first in 1998. Manufacturers scrambled to find a replacement, organic compounds made from rubber, glass, and metal fibers. The first non-asbestos pads braked worse, overheated at 750 degrees, and released the rotor. But it was a start. Today, the top choice is ceramic composites. The base is ceramic made from silicon nitride and silicon carbide, mixed with copper fibers for heat dissipation. The material withstands 650 degrees without deforming, doesn't squeal, and doesn't dust. Ceramic makes up 40 or 50% of the mass, reinforced with steel fibers for strength. At 500 degrees, regular pads smoke. Ceramic ones stay cool as ice. In this massive plant, something is born that'll save your life on the road. Manufacturing ceramic brake pads isn't just mixing powder with binder. It's precise science involving pressure, fire, and high-precision machinery. Each pad weighing 7 ounces has to survive 600 degrees of hell, not crumble, and not let go of the rotor. Let's break down the process step by step, from raw materials to finished kit. Everything starts with hoppers full of powders. The main ingredient, ceramic, meaning silicon nitride silicon carbide, a white powder hard as diamond. They add copper fiber for heat dissipation, thin threads the width of a hair, graphite for smooth grip, reinforced glass for strength, barium sulfate for stability at high temperatures. Each recipe is a factory secret, like the Coca-Cola formula. In giant mixers with a 500-gallon capacity, powders are combined in precise proportions. They add liquid wax-based lubricant, 5 or 7% by weight. The mixer spins for 30 minutes at 50 revolutions per minute, transforming dry powder into a uniform wet mass, like bread dough. Temperature is held at 100 degrees so the lubricant doesn't freeze. The result is raw dough weighing 1,100 pounds, ready for forming. The mass goes into a rotary press, a machine with 20 tons of force. They pour 550 grains of the mixture into a metal mold measuring 6 by 2.5 by half an inch. The top plate descends with 285,000 pounds per square foot of pressure, like parking a tank on your palm. In 10 seconds, the dough compresses into a monolithic green blank, 3/4 of an inch thick. The pressure squeezes out all the air, creating a density of 175 pounds per cubic foot. The press runs in cycles, 60 blanks per hour. Each comes out perfectly smooth with a friction surface angled at 5 degrees for better disc contact. The blank's still brittle as cheese, but it already has the shape of the future pad. The most critical stage, sintering. Green blanks go onto steel trays, 50 pieces each, then get pushed into a tunnel kiln 100 feet long. Temperature rises gradually. At peak heating, 4 hours in, the ceramic melts. Copper fibers fuse. Graphite crystallizes. Total sintering time, 12 hours. Finished pads, gray-silver monoliths. Go to inspection. A laser scanner checks dimensions accurate to 1/100th of a millimeter. Ultrasound checks density and cracks. 2% get rejected. Next, grinding. The machine removes 0.5 millimeter from the friction surface for perfect geometry. Edges get rounded to prevent squealing. They apply a protective coating, a thin layer of molybdenum disulfide for that first soft braking. Laser marked, then assembled into kits. 4 pads plus springs plus backing plate. The final test, the simulation stand. The pad is pressed against a disc spinning 2,000 revolutions per minute for 200 cycles. Acceleration, then hard braking up to 6,000 degrees. They check wear, squealing, dust. Ceramic pads pass without smoke. Metal ones squeal. A finished pad wears out after 30,000 miles. That's normal wear. With aggressive driving, it wears out after 18,000 miles. The U.S. market operates with 131 facilities, which has decreased by 0.6% in recent years due to automation. Production is tied to the automotive industry. Rising car sales drive demand, especially for pad replacements in trucks and passenger vehicles. Key trends: shifting to eco-friendly materials without copper. California capped it at 0.5% starting in 2025, which cut pollution by 28% statewide. Imports matter, but tariffs affect local production. The leaders are the southern U.S., specifically Texas, Alabama, Tennessee, with Ford and GM plants. The European brake pad market shows steady growth at an average annual rate of 4.7% through 2028. In Germany, the market leader volume will hit nearly $320 million by 2028. France is growing at 5.5% annually, the UK at 3.8%. Metallic pads are still popular and hold 25% of the EU market because they're cheap for trucks and Porsches. But their dust is a problem. Steel and copper settle on roads, get into water and lungs. Ceramic cuts emissions by 80% compared to these semi-metallics. Now, besides asbestos and metallic pads, there was an attempt to make organic ones. These are pads from the 2000s, the first mass replacement for asbestos. The base is synthetic rubber, fiberglass for reinforcement, Kevlar or aramid fibers for strength, plus barium sulfate and graphite. The soft compound gave a quiet bite. Little dust, didn't scratch rotors. But at 550 degrees, they lose 30% of their stopping power, which works for daily driving but not for sport. Hold a 1-inch tungsten cube. It weighs nearly 1 pound, denser than gold, heavier than lead. Drop it and the floor dents, not the cube. This metal refuses to melt until 6,192 degrees, hotter than Earth's core beyond temperature where other metals vaporize. Light bulb filaments, armor-piercing bullets, rocket nozzles, tungsten survives conditions that destroy everything else. Yet it starts as dull gray rock, looking worthless. How does brittle ore transform into metal that won't surrender? Why does one nation control 70% of global supply? Stay with us. You'll witness industrial-scale mining reshaping mountains and discover tungsten's shocking secret. This indestructible metal is so brittle in pure form it shatters like glass. The Dayu tungsten mine in Jiangxi, China dominates the landscape. An open pit 3 miles across descending 800 feet into earth. Giant haul trucks, each carrying 400 tons, crawl spiral roads looking like toys from rim's edge. This single mine produces 40,000 tons of tungsten concentrate annually, enough to manufacture 2 billion light bulbs. 70% of world's tungsten comes from Chinese operations like this. Watch the blast sequence. Drillers bore holes 50 feet deep in geometric patterns across the pit floor. Each hole gets packed with explosives, 200 pounds per hole, hundreds of holes per blast. The detonation ripples across the face in sequence, fracturing 10,000 tons of rock in 30 seconds. Dust clouds billow 300 feet high, visible from orbit. What took nature millions of years to create, humans demolish in half a minute. The ore, wolframite, and scheelite, contains just 0.5% tungsten. That means 99.5% is waste requiring removal. Massive crushers reduce boulders to gravel. Ball mills grind further. Rotating drums containing steel balls pulverize ore to powder finer than flour. The grinding noise is deafening, continuous thunder as metal crushes rock. Separation uses gravity and magnetism. Wolframite, being dense and magnetic, concentrates easily. Scheelite requires froth flotation. Chemicals make tungsten minerals hydrophobic, clinging to bubbles while waste sinks. The concentrate, now 15% tungsten, ships to processing plants. China's dominance isn't accidental. They control reserves, processing knowledge, and critically tolerate environmental damage Western nations won't accept. Tailings ponds stretch miles, filled with chemical-laced sludge that'll remain toxic for centuries. Processing concentrate into pure tungsten trioxide requires acid digestion. The concentrate gets dissolved in hydrochloric or nitric acid, violent chemical attack breaking molecular bonds. Tungsten dissolves while impurities precipitate out. The solution, now containing tungsten compounds, undergoes pH adjustment causing yellow tungsten trioxide powder to crystallize. This powder undergoes hydrogen reduction, the crucial transformation. Inside tube furnaces heated to 1,800 degrees, hydrogen gas flows over tungsten trioxide. The hydrogen strips oxygen atoms, leaving metallic tungsten powder. But here's the challenge. Pure tungsten powder is useless. The particles don't bond. Press them together and they crumble. Tungsten's ultra-high melting point makes conventional melting impossible. No crucible survives temperatures required. The solution? Powder metallurgy. Powder metallurgy bypasses melting through sintering. Particles fuse below melting point under pressure and heat. Tungsten powder gets pressed into desired shapes using hydraulic presses, generating 50,000 psi. The compacts, called green bodies, are fragile, handle roughly, and they disintegrate. The green bodies enter sintering furnaces operating at 4,500 degrees in hydrogen atmosphere. At these temperatures, tungsten atoms migrate across particle surfaces, welding together without liquefying. The process takes 12 hours. What emerges has transformed. The powder compact becomes solid metal with 99% density. Dimensional changes are predictable but significant. Parts shrink 18% during sintering. Engineers must design oversized greens compensating for this shrinkage. Pure tungsten remains problematic. It's brittle at room temperature, difficult to machine. The solution? Alloying. Adding 2% thorium or lanthanum dramatically improves workability. These elements prevent grain growth during sintering, creating fine-grained structure that machines more easily. The most common tungsten product worldwide is tungsten carbide, tungsten powder mixed with carbon, sintered together. Tungsten carbide achieves hardness second only to diamond. Cutting tools made from tungsten carbide last 10 times longer than steel equivalents. Mining drill bits, machining inserts, industrial dies. Anywhere extreme wear occurs, tungsten carbide dominates. The material cuts steel like butter but shatters under impact. Drop tungsten carbide block on concrete and it explodes into fragments. The combination of extreme hardness and extreme brittleness defines tungsten's paradox. Wire drawing demonstrates tungsten's remarkable properties. The sintered tungsten gets heated to 3,000 degrees and drawn through progressively smaller diamond dies. The wire diameter reduces from 1/4 inch to thousandths of an inch, thinner than human hair for light bulb filaments. This drawing process work hardens tungsten, increasing strength. Modern LED lights made tungsten obsolete for household illumination, but specialty applications remain. Electron microscopes, X-ray tubes, high-temperature furnace elements. Anywhere electricity must flow through extreme heat, tungsten wire delivers. The element's resistance increases with temperature, making it self-regulating. In light bulbs, hot filament resists current flow, limiting power draw and preventing burnout from voltage spikes. That wire glowing white-hot at 6,000 degrees, tungsten operating at 70% of its melting point, yet lasting thousands of hours. Military applications drive demand relentlessly. Tungsten's density, 19.3 grams per cubic centimeter, nearly identical to gold, makes it ideal for kinetic penetrators. Armor-piercing ammunition uses tungsten or tungsten alloy cores. Fired from tank cannons at 5,000 feet per second, these projectiles punch through steel armor through sheer mass and velocity, not explosive force. The ethical controversy is intense. Depleted uranium performs similarly but raises radioactivity concerns. Tungsten offers equivalent performance without radiation, but mining's environmental cost is staggering. Each ton of tungsten requires processing 200 tons of ore, generating mountains of toxic waste. The metal that survives Earth's most extreme conditions is extracted through processes poisoning the planet. Swedish chemist Carl Scheele identified tungsten oxide in 1781, studying the mineral scheelite. Spanish brothers Juan and Fausto El Huyar isolated metallic tungsten 2 years later. The name derives from Swedish tungsten, heavy stone. For a century, tungsten remained laboratory curiosity. Everything changed when Thomas Edison needed light bulb filaments in 1879. He initially used carbon, which burned out quickly. By 1904, manufacturers switched to tungsten, revolutionizing electric lighting. World War I revealed tungsten's military value. High-speed steel cutting tools containing tungsten enabled mass production of weapons. Today's annual production exceeds 90,000 tons, with China dominating supply chains so completely that Western nations consider tungsten a strategic vulnerability. Carbon emissions remain problematic as tungsten production generates 8 tons of CO2 per ton of metal, primarily from energy-intensive processing. Recycling exists but remains limited. Only 30% of tungsten gets recycled, far below rates for aluminum or steel. Here's the secret we promised. Tungsten's incredible strength comes from its weakness. Pure tungsten is brittle, shattering easily. But that brittleness stems from its crystal structure. Atoms packed so tightly that dislocation movement, the mechanism allowing metals to deform, essentially stops. This atomic rigidity creates the highest melting point, extreme hardness, and resistance to deformation. The metal survives temperatures melting steel because its atoms simply refuse to move. Adding trace elements creates enough flexibility for workability while maintaining strength. From Chinese mountains to cutting edges worldwide, the transformation completes. We've mastered metal that defies conventional metallurgy, processing it through techniques developed when melting proved impossible. That drill bit cutting through rock, that filament glowing white-hot, that bullet-piercing armor, all share tungsten's fundamental contradiction. The strongest metal is also the most fragile. The element that won't melt is useless without powder metallurgy. We've learned to work with nature's extremes by accepting, not fighting, inherent limitations. Tungsten doesn't compromise. Neither do the engineers who've learned to shape it.
The metal that protects all other metals from rust. Picture this: 70% of the world's steel is covered with a thin layer of zinc. Bridges, skyscrapers, cars, ships. Everywhere, zinc stands guard, taking the hit from corrosion. Every second, the world produces 1.5 tons of zinc, 14 million tons per year. It's the 4th largest metal by production volume on the planet, after iron, aluminum, and copper. But they extract it unusually. Zinc is vaporized at 1,800 degrees Fahrenheit, and the vapor is collected. Yes, the metal turns into gas. How do they turn gray ore, mined a mile underground, into a bluish-silver metal that sacrifices itself for others? You'll learn why the ore burns in furnaces, how they collect metallic vapor, and why without zinc, the entire infrastructure of the planet would collapse. Watch till the end. The finale will show what's behind every galvanized beam. This is the story of the bodyguard metal that took on the corrosion of the entire world.
A mile underground, darkness, explosion, tons of rock crash down. This is a zinc mine, one of hundreds around the world where ore for the guardian metal is extracted every day. Underground dump trucks with 50-ton capacity haul ore to the mine shaft. An elevator the size of a house lifts the rock to the surface. The ore is dark, almost black. This is sphalerite, zinc sulfide. Crystals with diamond-like brilliance, but the metal content is only 10 to 15%. The rest is waste rock. Trucks carry the ore to the processing plant. The transformation from stone to metal begins. Massive cone crushers as tall as a 3-story building grind ore chunks the size of cars. The noise is deafening. The rock is crushed into gravel the size of fists. Then the gravel goes into ball mills, rotating steel drums 16 feet in diameter, filled with steel balls the size of watermelons. The drum rotates, balls fall, grinding the ore into fine powder. After 8 hours of grinding, you get gray dust, particles the size of sand grains. The ore powder is mixed with water, creating gray liquid slurry called pulp. It's pumped into huge flotation machines, tanks with volumes of 3,500 cubic feet. Chemical reagents are added, foaming agents and collectors. Mixers are turned on and air is fed from below. The magic of flotation begins. Millions of air bubbles rise through the pulp. Particles of sphalerite, zinc ore, stick to the bubbles and float up. A gray foam forms on the surface, 20 inches thick. This foam contains zinc. Waste rock settles to the bottom and is drained off. The foam is collected, filtered, dried. The result is concentrate, powder containing 50 to 60% zinc. From 100 tons of ore, you get 10 to 15 tons of concentrate. This concentrate is loaded into rail cars and shipped to the smelting plant. There begins the real alchemy, turning powder into molten metal. And this is a process where metal turns into vapor. At the plant, concentrate is loaded into fluid bed roasters, massive steel cylinders 66 feet tall. Hot air under pressure is blown in from below. The concentrate powder lifts up, floating in the air like dust. Gas burners are ignited. Temperature rises to 1,650 degrees Fahrenheit. The zinc sulfide ignites. Yes, the ore burns. Sulfur oxidizes, releasing enormous amounts of heat. Sulfur gas flies up the stacks. It will be captured and turned into sulfuric acid. And zinc sulfide transforms into zinc oxide, a gray-white powder. The temperature in the furnace is so high that the walls glow red. The roasted concentrate, zinc oxide, is cooled and mixed with coke, crushed coal. The proportion, 3 parts oxide to 1 part coke. This mixture is loaded into vertical retort furnaces, steel towers 50 feet tall, lined inside with refractory silicon carbide. Heating begins. Temperature starts climbing. 1,800 degrees, 2,000 degrees, 2,200 degrees. At 2,200 degrees Fahrenheit, carbon begins taking oxygen away from zinc oxide. A reduction reaction occurs. But something amazing happens. Zinc doesn't melt. Its boiling point is only 1,665 degrees, but the furnace is at 2,200. So zinc immediately turns into vapor, metallic vapor. Inside the furnace, atoms of gaseous zinc are flying around. The vapors rise up and exit the furnace through piping. They enter a condenser, a special cooled chamber. Temperature in the condenser is around 840 degrees, below boiling point but above melting point of zinc. The vapors condense. Drops of molten zinc settle on the condenser walls, glowing orange. Liquid metal flows down the walls and collects in a receiver. This is crude zinc, contains impurities of lead, cadmium, iron. Purity around 98%. Each furnace produces up to 100 tons of zinc per day. The metal is cast into molds. The result is ingold bars weighing 55 pounds each, silver gray with a bluish tint. For some applications, pure zinc is needed. Then it's refined, purified by distillation. Crude zinc is heated to boiling in a vacuum furnace. Under reduced pressure, boiling point drops to 1,300 degrees. Zinc vaporizes while impurities remain solid. Zinc vapors are condensed in a cooler.
The result is refined zinc with 99.99% purity. This zinc is cast into ingots. On the ingot surfaces, a characteristic pattern forms, crystalline designs resembling frost flowers on glass. This is called zinc flowers. Ingots are stacked. Zinc is ready for use, but its main application awaits in hot-dip galvanizing baths. There, steel products will receive corrosion protection. The process looks impressive, like baptism of metal by fire. A steel beam 40 feet long is immersed in a bath of molten zinc. Temperature 840 degrees. The beam completely disappears in the silvery liquid. Chemical reaction begins instantly. Zinc reacts with iron on the steel surface, forming a layer of intermetallic compounds, a solid alloy of zinc and iron. This layer bonds permanently to the steel. On top, a layer of pure liquid zinc. The beam is held in the bath for 1 to 2 minutes. Then it's pulled out. Excess molten zinc drains back. In air, the coating quickly solidifies. The surface becomes silvery, matte, with the characteristic pattern of crystals, zinc flowers. Coating thickness from 2 to 8 thousandths of an inch. That's just fractions of an inch, but it's enough. The galvanized beam won't rust for 50 to 70 years. Even scratches aren't scary. Zinc continues protecting. It's about electrochemistry. Zinc is more active than iron. When corrosion begins, zinc oxidizes, not steel. Zinc sacrifices itself, protecting iron. This is called cathodic protection. World production of galvanized steel, 55 million tons annually. This uses 6 million tons of zinc. Without zinc, modern cities would be impossible. 70% of zinc goes to protecting steel. But there are other applications. Brass, an alloy of copper and zinc, has been known for thousands of years. Contains 15 to 45% zinc. Golden, strong, easily worked. Brass is used for plumbing fixtures, musical instruments, cartridge cases, decorative items. Zinc die casting, a method for manufacturing complex parts for automotives and electronics. Molten zinc is injected under pressure into steel molds. The result is complex-shaped parts accurate to tenths of thousands of an inch. Zinc batteries, still used by the billions. Zinc powder in chemical industry. Zinc oxide in rubber industry, cosmetics, medicine. Zinc ointment heals wounds. World zinc mining, 14 million tons per year. China produces 40%, 5.5 million tons. Peru, Australia, USA, India, other major producers. Zinc price, around $3,000 per ton. The history of zinc as a separate metal began late. Europeans knew brass since ancient Rome, but couldn't obtain pure zinc. The problem, zinc evaporates when heated. Indian and Chinese metallurgists in the 16th century learned to condense zinc vapors in closed retorts. In Europe, pure zinc was obtained by German chemist Andreas Markgraf in 1746, but mass production began in the 19th century. Revolution happened in 1836 when French engineer Stanislas Sorel discovered the hot galvanizing process. He found that immersing steel in molten zinc protects from corrosion. This changed construction forever. Before galvanizing, steel structures rusted within years. With galvanizing, they serve for decades. The Eiffel Tower is painted, but many bridges from that era are galvanized and still standing. Today, without galvanized steel, skyscrapers, bridges, power lines, ships are impossible. Zinc, the invisible guardian of infrastructure.
And so, having traveled from explosions a mile deep through giant crushers and flotation tanks, through fluid bed furnaces at 1,650 degrees and retort towers at 2,200, through transformation into metallic vapor and condensation, zinc emerges, the bodyguard metal of modern civilization. The silvery metal that sacrifices itself, protecting steel from rust. the fourth largest metal by production on the planet, without which all infrastructure would collapse. Every time you see a steel bridge beam, a roofing sheet, or a car body, know they're protected by a thin layer of zinc as thick as a human hair. A layer that takes on corrosion, oxidizes instead of steel, slowly destroys itself, saving the structure. This is a story of nobility at the atomic level, how one metal protects another, sacrificing itself. From underground explosions to silvery skyscraper beams, zinc's journey spans several weeks and 2,200 degrees. The metal that vaporizes to protect, that oxidizes so others don't rust. The invisible shield of 14 million tons annually, standing between steel and corrosion. Zinc. This is why bridges don't collapse, roofs don't leak, and cars don't turn to dust in 5 years. The guardian metal, the sacrificial metal, the metal without which the modern world would simply fall apart from rust.
Every year, the world melts over 1 billion tons of pig iron. But where does all that fiery metal come from? Imagine a giant furnace as tall as a 35-story skyscraper that never sleeps. Its guts glow like the Earth's core, and the temperature hits 3,600 degrees Fahrenheit. That's 2,000 Celsius. This is a blast furnace. They don't just melt metal here. They give birth to the heart of industry. But there's a secret that only the guys standing at the tap hole know. If you stick around to the end, you'll find out what's really happening in the center of this burning fortress, and why it changes everything. Imagine a colossal tower, taller than a 35-story skyscraper. The ground beneath your feet vibrates slightly from its relentless work, and the air is filled with a hum, like the breathing of a giant beast. At night, its top glows, pushing back the darkness. This is a blast furnace, a massive vertical smelter, where 24 hours a day, 7 days a week, the magic of turning ore into metal happens non-stop. Why blast furnace? The name comes from the process itself, and it's no accident. The whole secret to a blast furnace is the constant blast of incredibly hot air that fuels the fire and kicks off all the necessary reactions. If you were to slice a blast furnace open, you'd see it looks like a stretched out bottle. Every part of it has a name and a purpose. The walls of the furnace are lined with special refractory bricks, capable of withstanding temperatures that would melt solid rock. This is a true fortress, built to tame fire itself. So what do they feed into this fiery throat? The process is like cooking from a very strict recipe. The mix of ingredients loaded into the furnace is called the charge. Here are its main components: iron ore, fuel, coke, and fluxes. These three ingredients are loaded into the furnace in precisely measured layers. A layer of coke, then a layer of ore with fluxes, then coke again, and so on. Every few minutes, a new batch weighing tens of tons is sent into the furnace. The iron ore is the foundation of it all. They usually don't just use raw ore dug from the ground, but specially prepared sinter or pellets. These are baked clumps of fine ore, or rolled balls of ore concentrate. The main goal is to have as much iron oxide in the raw material as possible, from which the oxygen will later be ripped out. Coke is coal that's been cooked in special ovens without access to air. After this treatment, it becomes strong, porous, and burns with an immense amount of heat. But that's not its only role. The carbon that makes up coke is the real magician that turns ore into metal. The flux is most often ordinary limestone. Why is it needed? The ore and coke always have useless impurities, so-called gangue. The limestone helps to bind these impurities, forming an easily meltable slag. So, the charge is loaded. What's next? This is where it gets interesting. Two streams move towards each other. From the top, the layers of the charge slowly descend, and from the bottom, a hurricane of superheated gases rushes up to meet them. It all starts at the bottom, in the hearth. Through special pipes called tuyeres, air heated to a scorching 2,200 degrees. Fahrenheit, 1 to 200 Celsius, is blasted into the furnace under huge pressure. That's hotter than volcanic lava. Meeting the red-hot coke, the oxygen in the air instantly ignites. The temperature in this zone skyrockets to 3,600 degrees Fahrenheit, 2,000 Celsius. This creates carbon dioxide. But as it rises higher and passes through new layers of coke, it turns into another gas, carbon monoxide. And this gas is the real oxygen thief. As this searing hot stream of gas rises up the furnace shaft, it envelops the chunks of ore and begins to greedily rip the oxygen from them, leaving behind reduced, spongy iron. The reduced iron continues its journey downward into hotter and hotter zones. It passes through the glowing layers of coke and, like a sponge, begins to soak up its carbon. And here's where something amazing happens. Pure iron melts at a very high temperature of 2,800 calories, 1,530 nanometers. But soaking up carbon dramatically lowers that melting point. That's why a blast furnace doesn't produce pure iron, but an alloy of iron and carbon, pig iron, which becomes liquid at just 2,200 nanometers, 1/200 nanometers. Roughly every 40 to 60 minutes, enough liquid products have collected in the bottom of the furnace. It's time for the climax, a truly mesmerizing sight. A furnace worker, the keeper, uses a special drill to punch open a hole in the furnace wall, the tap hole. First, they tap the slag. It's lighter than the iron, so it floats on top. It's a molten, lava-like mass that flows into special ladles. And then they open the iron tap hole, and a dazzling, sparking stream of molten metal erupts with a roar. This is the River of Fire. The temperature of this stream is around 2,700 degrees Fahrenheit, 1,500 Celsius. It flows down special troughs, bathing everything around in a blinding light, and fills giant ladles that look like railway tankers. Each of these ladles holds hundreds of tons of liquid metal. From here, the pig iron will be sent to its next stage, either poured into molds, or, more often, sent for further processing into steel. A blast furnace is an amazing operation that produces more than just pig iron. The byproducts are just as important. The blast furnace slag, which we've already mentioned, becomes a valuable raw material for making cement, building blocks, and road aggregate after it's cooled and crushed. The blast furnace gas that comes out of the furnace isn't just released into the atmosphere. It's cleaned of dust and used as fuel to heat the very same air that's blasted back into the furnace. It's a closed-loop system that makes the process more economical. Without a doubt, metallurgy is a serious challenge for the environment. However, modern technologies are constantly evolving. When blast furnaces are modernized, powerful filters and cleaning systems are installed to capture dust and harmful gases. Scientists and engineers around the world are working on creating green technologies, like using hydrogen instead of coke, to make metal production cleaner. But for now, the blast furnace remains the king of metallurgy. And every time you see a bridge, a skyscraper, or a train, remember these fiery giants and the people who tame rivers of fire to give the world a strong and reliable foundation. For 75 years, from the late 19th century to the 1970s, the USA was the undisputed world leader in the production of pig iron, steel, and rolled products. During this period, the American iron and steel industry wasn't just a sector of the economy, it was the key, or barometer, of the American economy. In the 1920s, for example, the country produced about half of the world's pig iron. Imagine that. Every other ton of this strategic metal in the world was born right here in American furnaces. Imagine a magnet so powerful it can lift a weight 1,000 times its own. How can a piece of metal stop a jet engine turbine or become the heart of a Tesla electric motor? The secret lies in rare earth elements, materials that hide more mysteries than gold or platinum. To create a single neodymium magnet, you have to move mountains of ore, melt metal at over 2,700 degrees, and use technologies that resemble alchemy. But there's a detail that almost no one knows about. Watch till the end, and you'll learn a secret that will change your understanding of the power of metal. The mining and initial processing of rare earth ores are a key stage in the production of neodymium magnets, as this is where the foundations for obtaining the necessary components are laid. This process begins with the large-scale mining of ore, containing the rare earth elements that make up neodymium. In the first stage, the ore is extracted from the earth using various mining methods. This can be either open-pit mining or underground mining, depending on the depth and type of the deposit. After extraction, large chunks of ore are delivered to crushing plants. At the crushing plants, the ore undergoes primary crushing. Large boulders of ore pass through a series of crushers that gradually reduce their size into smaller fractions. This is necessary for further effective processing and extraction of valuable components. The crushed ore may then be fed into mills for further fine grinding into a powder or a pulp, which consists of fine ore particles suspended in water. The next critically important stage is ore enrichment, the purpose of which is to separate the rare earth minerals from the waste rock. This process can involve various methods. One of the most common methods involves mixing the crushed ore with water and special reagents. These reagents selectively attach to the surface of the rare earth minerals, making them water repellent. Air is bubbled through the mixture, creating bubbles to which the hydrophobic minerals adhere and rise to the surface, forming a froth that is then collected. Heavier particles settle faster, allowing them to be separated from the lighter ones. Some rare earth minerals have magnetic properties, which allows them to be separated from non-magnetic components using magnetic separators. After enrichment, a concentrate is obtained, which contains a much higher concentration of rare earth elements. However, this concentrate is still not a pure metal. It requires further chemical processing, which usually includes dissolving the valuable components with acids or alkalis, precipitation, solvent extraction, and ion exchange chromatography. These processes allow for the separation of each rare earth element individually and its purification to a high degree. For example, neodymium is separated from other rare earth elements like praseodymium or samarium. The final result of this complex chain of processes is the production of high-purity neodymium oxide, which is then reduced to metallic neodymium. This metallic neodymium, in the form of granules or ingots, is ready for the next stage, alloying with other components to create powerful neodymium magnets. The entire process requires strict quality control and significant energy expenditure, but is absolutely necessary to obtain the raw material for the production of these strategically important materials. After the careful extraction and purification of rare earth elements, particularly neodymium, comes one of the most crucial stages in the production of high-performance neodymium magnets: alloying. This process demands extreme precision and control, as the final microstructure and, consequently, the magnetic properties of the finished material depend on it. The purified metals, neodymium, iron, and boron, are carefully weighed in strict proportions. These three elements are the main components of the alloy, providing its unique magnetic characteristics. In addition to them, small amounts of other elements, such as dysprosium, terbium, cobalt, or copper, may be added to the alloy. These additives are introduced to achieve specific properties, for instance, to increase the magnet's temperature stability, improve its resistance to demagnetization, or modify the material's brittleness. The exact composition of the alloy is a trade secret for many manufacturers and varies depending on the desired final characteristics of the magnet. The weighed components are placed in a specialized vacuum induction furnace. The use of a vacuum is critically important as it prevents the oxidation of the rare earth metals and other components at high temperatures. Oxidation would lead to the formation of undesirable phases, which would degrade the magnetic properties of the material. Induction heating ensures rapid and uniform melting of all components, creating a homogeneous melt. The melting temperature in such a furnace can reach over 2,700 degrees Fahrenheit. After achieving a complete melt and homogenization of the alloy, the stage of rapid cooling, known as the strip casting method, begins. This is a key moment for forming the optimal microstructure. The molten metal is poured in a thin stream onto a rapidly rotating, cooled drum. Contact with the cold surface of the drum leads to an extremely rapid cooling of the melt at a rate of up to millions of degrees per second. This extremely rapid cooling prevents the formation of large crystal grains and allows for the formation of an amorphous or microcrystalline structure. Instead of the typical crystalline structures formed during slow cooling, extremely fine grains are formed. This process is also known as rapid solidification, and it is fundamental to achieving high magnetic properties. The resulting material takes the form of thin, easily crumbled flakes or ribbons. This unique microstructure, with very fine, often anisotropic grains, is the key to the high strength of neodymium magnets. The smaller the grain size, the more difficult it is for the magnetic domains to change their orientation, which provides high resistance to external demagnetizing fields. Thus, the alloying and rapid cooling stage is fundamental for forming the magnetic characteristics that will later be locked in during subsequent production stages. Then there are two paths: either long-term dry storage in double-walled concrete containers or reprocessing. That happens in other countries, as the US mostly stores rather than reprocesses. In dry storage, the assemblies stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This isn't the end, but a new stage of life, slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Transportation is under guard on a special route with an escort, GPS, and mandatory 2 seals, 3 codes, and a dosimeter on every side. Because even in its peaceful form, this is dangerous stuff that commands respect. After all is said and done, what's left is the depleted uranium hexafluoride. They call it tails. It's a mix of isotopes that still has a little U-235, but not much. These tails are stored in steel barrels, in special supervised yards. But in the future, they could be reprocessed in next-generation reactors, squeezing out every last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It's removed, carefully by a robotic system, and moved into pools of water. The depth is over 20 feet. The water cools it and shields the radiation because the fuel is still hot, both physically and radioactively. There it rests for several years. Next, the pellets are sintered in furnaces at almost 3,000 degrees to make them as strong as porcelain. Then they're polished and ground. Perfect dimensions are crucial for a tight fit inside the cladding. The pellets are loaded into long metal tubes. Fuel rods, usually made of a zirconium alloy because it doesn't rust, doesn't react with water, and can withstand insane radiation. Each rod holds over 300 pellets. The rods are hermetically welded shut and bundled into modules, fuel assemblies. They look like a frame of several dozen tubes gathered into a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly comes testing for leaks, uniform filling, weld integrity, and behavior under temperature. There are no small details, because any one of them could cost not just money, but lives. The finished fuel is packed into armored containers that can withstand impacts, fires, and falls from a height. But one centrifuge isn't enough, so they're connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so it goes, cycle after cycle, until the U-235 content reaches at least 3 or 5%. That's the reactor grade standard. For weapons, of course, they follow entirely different routes, which are classified and under strict international control. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark gray color. This powder is pressed under 20 tons of pressure into small cylindrical pellets, 3/10 of an inch in diameter. They look almost cute. But each of these little pills holds an energy equivalent to 17,000 cubic feet of natural gas. And so, mission accomplished. The dust has been turned into a gas, ready for the most interesting part, isotope enrichment. But don't get too excited yet. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think a washing machine spins fast? You haven't seen nuclear centrifuges that do 70,000 revs a minute. That's 10 times faster than a jet engine turbine. And all for one thing: to separate uranium isotopes. Uranium hexafluoride, that same toxic gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms are flung to the edge, while the lighter U-235 atoms stay closer to the center. A tiny microscopic difference, 1% in mass, and all this explosive technology spins just for that. That means you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It's extremely toxic. It corrodes metals, destroys skin, and in moist air, it instantly turns into hydrogen fluoride and uranic acid. Basically, a deadly cocktail. That's why this is all done in sealed, automated reactors that look more like devices from an evil genius's lab. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, watching the gauges. Any mistake, boom or hiss, and you're in a hazmat suit scrambling for the decontamination shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, drums with engravings, batch numbers, and a radioactive sign. Each one weighs up to 14 tons. Yellowcake is packed into double-walled drums, loaded onto escorted trailers, plastered with radiation signs, and off it goes to an enrichment plant. It's from this toxic dust that the journey begins, the one that leads to the white light of a lamp over your kitchen table, or the electricity in the subway hurtling beneath New York. Right then, the yellowcake has arrived, in drums, radioactive and dry as a desert wind. The next step, turn it into a gas. And not some lavender-scented air freshener, but uranium hexafluoride, the very same stuff from which the required isotope for reactors and other things is later separated. Let's cook, baby! The uranium concentrate is first dissolved in acid, purified, filtered from impurities, converted into uranium dioxide. And this is where the magic starts. The uranium dioxide is treated with fluorine in special reactors at a temperature of 1,000 degrees. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees. The rest is mostly useless mass that doesn't work in a reactor. And to squeeze the required drop of energy from it, hundreds of tons have to be processed. That's why they say nuclear energy is quite the marathon. After mining, the ore is crushed, milled, and thrown into a chemical bath. Acid or alkaline solutions are added, which extract the uranium like coffee from a filter. Then comes filtering, precipitation, and drying at 500 degrees. And what comes out is yellow cake, a yellow powdered concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellow cake. It looks pretty, mustard-colored, fluffy, like a spicy powder for a Barbie. But God forbid you breathe it in or touch it. Alpha radiation, a long half-life, dangerous dust that gets into your lungs and settles there forever. It's handled only with respirators, suits, and behind 3 layers of glass shielding. It all starts in the dust. And that's not a figure of speech. Uranium ore is mined in hot, arid regions. Arizona, Wyoming, Texas, New Mexico. Think cowboy country, but instead of lassos, they have drill rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is a scorcher, up to 100 degrees Fahrenheit in the shade if you can find any. There are 2 ways to get it. Open pit mining, where they strip the topsoil and haul the ore out with excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. Then there's the in situ leaching method. Pipes are driven into the ground, special solutions are pumped in to dissolve the uranium straight from the rock, and then it's all pumped back out. All this ore, a gray-brown rock, looks no different from ordinary stone. But inside it, uranium-235 makes up only 0.7%. What could be scarier than dust that glows with an invisible light? A rock that looks like ordinary gravel, but holds the fuel for power stations that light up megacities. So why is uranium called an energy marathon? Because to get just a few grains, you have to move hundreds of tons of earth, boil ore in acids, and turn it into a yellow powder that can kill with a single touch. And this is where the real alchemy begins. Toxic dust becomes a gas, and that gas becomes energy. But there's a detail they don't talk about publicly, and you'll only find it out at the end of this video. Every year, dozens of nuclear submarines are launched into the world's waters. Giants capable of diving to depths of over 2,000 feet and remaining invisible for months. These are truly underwater cities with a reactor at their heart, hundreds of tons of steel and titanium alloy, and incredible silencing systems that absorb sound. But how is such a machine born from cold metal? What secrets does its construction process hide, where even a microscopic crack can cost lives? Watch carefully. In the finale, you will learn what is usually hidden behind the 7 locks of military archives. A nuclear submarine is a complex engineering creation, the development of which begins long before the first sheet of metal hits the machine tools. It all starts with computer-aided design. At this stage, several key parameters are considered: the size and shape of the hull, the power supply system, weaponry, and noise reduction measures. The length can range from approximately 300 to 560 feet depending on the class, and this directly affects the diving depth. The most advanced submarines can descend to 1,968 to 2,460 feet, and some experimental models, even over 3,000 feet. Based on the initial designs, physical models of the submarine are created, which are tested in special water tunnels. This helps engineers see how the hull shape affects maneuverability, water resistance, and noise level. In parallel, computer modeling allows predicting how the submarine will behave underwater at different speeds and maneuvers. After simulations, when all calculations match up, the blueprints are sent to production. This is where the most interesting part begins: the actual assembly. For the construction of nuclear submarines, special materials are used that can withstand high pressure at great depths and provide protection against corrosion. Usually, these are high-quality steel or titanium alloys. Steel is cheaper and easier to produce, and it withstands pressure and impacts well. Titanium has the advantage of high strength, lightness, corrosion resistance, and being non-magnetic, which makes it harder to detect the submarine. However, titanium is more difficult to process and weld, as its melting point is higher, about 3,092 degrees Fahrenheit versus approximately 2,552 degrees Fahrenheit for steel. Before construction begins, the metal sheets undergo heat treatment. They are heated, rapidly cooled, and treated with special anti-corrosion compounds. The hull of a modern submarine is usually made of modular sections. This makes construction easier. Metal sheets are cut by giant laser and plasma devices with millimeter precision. Then, each sheet is bent under a press to give it the required shape. Often, some hull elements have a spherical or cylindrical structure. The sections are assembled separately. These are huge rings, or compartments, which are later joined in the final stage. This division into sections allows for working on different parts of the submarine in parallel, speeding up the construction process. When all the parts are ready, one of the most critical stages begins: welding the hull. The welds must be extremely strong. Even a microscopic crack at depth can cause a catastrophe. Therefore, automated electron beam welding is used, which allows for creating the most uniform seams possible. Additionally, each seam is checked with ultrasonic scanners and X-rays. Most nuclear submarines have a double hull. A strong inner hull withstands high pressure at great depth, while an outer hull provides a streamlined shape, improves hydrodynamics, and helps reduce the likelihood of detection. Ballast tanks, which regulate the submarine's buoyancy, are usually located between the hulls. To keep the submarine as stealthy as possible, it is covered with anechoic layers. These are polymer tiles that absorb sound waves, as well as composite materials with micropores that reduce the acoustic signature, and noise-dampening coatings applied to the propellers and power plants. When all the hull sections are ready, their joining begins. Giant cranes move the compartments into special docks, where they are connected using bolted joints and welding. Next, the hull is tested for leaks by filling it with compressed air and checking for any escape. And strength tests are conducted in a hydrostatic tank, where pressure similar to deep sea diving conditions is simulated. After assembling and checking the hull strength, the key element is installed: the nuclear reactor. This is the heart of the submarine, allowing it to stay underwater for months or even years. A nuclear reactor is not just an engine, but a whole complex of energy and auxiliary systems that occupies a significant part of the submarine. Modern nuclear submarines use reactors that operate on the principle of heating water to produce steam. The fuel, usually enriched uranium-235 or uranium-238, is located in the reactor core. During the nuclear reaction, heat is released, which heats water in a closed loop. The hot steam is directed to turbines, which generate electricity and drive the propeller. The reactor is delivered in special protective containers and installed by a crane through an upper hatch in the hull. Inside, a compartment is provided for it, surrounded by materials that minimize radiation. Emergency cooling systems and sealed barriers are also located there. The reactor is mounted on a shock-absorbing platform that reduces vibrations and impacts during the submarine's movement. Then, heat exchangers and steam generators are installed, which are responsible for the circulation of the coolant, and turbines and electric generators are mounted. The functioning of all the submarine systems depends on their operation. Finally, the reactor compartment is sealed with multi-layered lead and composite panels to protect the crew from radiation. To check the readiness of the structure, the first startup of the reactor is carried out in test mode. The power is gradually increased, the radiation level in the compartments is monitored, and the cooling systems are tested at maximum loads. When the reactor is already installed and the submarine has a fully formed hull, it is still not ready for service. Inside, there are still only empty corridors and compartments, so the next stage is the installation of control systems, life support, weaponry, and crew quarters. Sonar systems are mounted in the bow and along the hull. They track enemy ships and scan the seabed. A computer system and automated combat control stations are also installed, ensuring maneuvering accuracy. Of course, weapon systems are also mounted. Torpedo tubes are located in the front part of the submarine, and they usually have automated reloading mechanisms for quick preparation of new shots. On strategic submarines, missile silos with hydraulic locks and pressure control systems are installed in the central part, which allow for launching missiles even at great depths. Since the crew can spend months underwater, the submarine must be as autonomous as possible. For this, nuclear submarines are equipped with oxygen generation systems, carbon dioxide removal, heating, ventilation, and a sufficient supply of water. If you've seen capsule hotels, then inside a submarine, there is something similar: sleeping capsules for the crew to rest. In addition, there are dining areas with significant food supplies and a command center with control panels, maps, and communication equipment. After arranging the living area, the submarine is almost ready to go to sea, but a series of complex tests are still ahead, which must prove that it can withstand colossal pressure, remain inconspicuous, and is maneuverable in extreme conditions and capable of performing combat missions. Such checks last from 6 months to 2 years and include both factory testing and combat training for the crew. First, the submarine is checked again for leaks. All electrical and navigation systems are tested, and the reactor is started up again. After this, the submarine goes to the open sea for the first time, where stabilizers, hydraulic cylinders, and steering mechanisms are checked. Sharp turns, dives, emergency maneuvers are practiced, and the maximum speed is determined, usually 25 to 35 knots, which is about 29 to 40 miles per hour. Then the submarine descends to periscope depth, about 65 feet, to assess stability. At greater depths, the operation of the ballast tanks under load is checked, and the submarine is gradually brought to its maximum permissible depth, which is about 1,968 feet, depending on the class. The reactor is necessarily tested under maximum load. When the submarine confirms its seaworthiness and reliability, they move on to testing the combat systems. The first shots are usually performed with training torpedoes, without a warhead. On strategic submarines, a launch of one ballistic missile may be conducted with a launch dive disarm in the air trajectory. On tactical submarines, the launch of cruise missiles like the Tomahawk or its analogs is checked. In addition, the submarine enters a special zone with hydroacoustic sensors, where specialists measure the noise level at different speeds and check the effectiveness of the noise dampening coating. Finally, the submarine undergoes a simulated combat mission, during which the crew demonstrates its readiness for real service.